Starting from this equation here, I am going to solve it, and when I integrate this, I need to make sure I include a term that is a constant term. So the r and the c are constants outside, so they're unaffected. And then there's a natural logarithm of, put it like that, natural logarithm of the charge q, because when you integrate dq over q, that's what you're going to get as the natural logarithm. Clean that up. I'm going to say plus a constant k. All right, and so I could argue that it's like this, but since it's just some arbitrary constant, whether it's multiplied by RC or not doesn't really matter in this case. So I'm going to just say minus RC ln times the absolute value of q plus some constant k. What I'm going to then do is divide both sides by minus RC. And so where that leaves me is, I'll say, okay, I have minus t divided by RC equals minus ln of q plus some constant c, and the reason I'm calling it c and not k is because I don't want to call it c. I'll call it something else. I call it, c looks like a capacitor. Got to be careful what symbols I use. I'll call it d, something we don't have yet. And the reason I'm using d is because when you divide k by RC, you're going to get a different constant than k. I'm just trying to be a little bit cleaner and not make it seem like this RC just goes away when I'm dividing it by the k. It's creating a new constant d for what it's worth. All right, so how do I get rid of this natural logarithm? The way I do that is I raise everything to the power of e. So I'll say e to the minus t divided by RC equals e to the minus ln of q plus d. All right, I'll make my e's red so you see that I'm just saying I'm going to raise both sides of that equation to e. Then that becomes e to the minus t divided by RC equals e to the minus, oh, there's no minus ln, sorry. E to the ln so this constant d is now e to the d, so it's just another constant. This is still a constant. All right, so what does this mean? This becomes q, let me save that for the right-hand side. This is still e to the minus t over RC. Over here I have, it's equal to e to the ln of q is just q, and I'm multiplying it times e to the d, which is now another constant. So what I'm going to do is I'm going to divide both sides. This may bother some of you. And by the way, this is q as a function of time. Charge changes. This is telling me how the charge changes. But initially, the charge is going to be an initial value. So if I bring this constant over to this side, I'm going to call this constant, which is now e to the minus d, because I'm dividing by it on both sides. I'm going to say that it's equal to q0. Why did I do that? Because initially, my charge at time 0 is going to be equal to q0. It's going to be equal to my initial charge. And so I have to have it start somewhere. If I didn't put this in here, and I put a 0 in there, e to the 0 is just 1. So my initial charge would just be 1, which doesn't make sense. But it it has to be some value of charge, which isn't necessarily 1 coulomb or whatever the unit is. So I'm going to say that my constant is Q0. So my full equation then becomes, for my capacitor, Q of t equals Q0 e to the minus t divided by RC. That's my equation. It tells me how my charge varies on my capacitor. All right. Now usually, and as I said, at time 0, it's my initial value Q0, which is this up here. Now usually, we're not that able or interested to find the charge. We're more interested in the voltage. Well, I know that Q is equal to the capacitance times the voltage. I'll say this is Q as a function of time. So I'm going to write it like this. All right, because voltage changes with time, the capacitance doesn't. The capacitance is going to stay the same no matter what the charge is on it, no matter what the voltage is across it. It should stay the same. So what I'm going to do then is I'm going to say wherever I see a Q, I'm going to put Q equals CV. So I'm going to do that substitution everywhere. All right, this is that equation we always use to relate charge, capacitance, and voltage. So my Q0 is going to be equal to C times my initial voltage, which is my battery voltage. And then I can divide both sides by my capacitance here. And this now is much more useful. This equation now tells me how my voltage across my capacitor is going to vary with time. That is a useful result. And that is where I'm going to end, and we're going to do some examples using this equation. We'll see how useful this equation is, but you saw this equation in lab. This basically tells us how quickly the voltage is going to drop from its initial value down to 0, and it's an exponential function, which is really neat to see, and you'll actually plot it for your capacitor. And you'll see how whether you actually get this curve. You should get something like it when you plot your voltage across your capacitor as a function of time as the voltage is draining or as the current flows through the resistor and the voltage and the charge are draining out of the capacitor. Okay, that's all for now.